My name is Hank Wotechko, and I'm a cloud engineer with Classy Design USA. We move business systems to the cloud with speed and accuracy. The performance issue that I'm going to be talking about is going to take on the appearance of a storage I/O performance bottleneck, when in fact it really isn't. It's something else, and we'll find that out together. The important thing to note here is that if you have a performance issue with your business application and you move it to the cloud thinking that you're going to solve that performance issue when it gets to the cloud, you might find that your costs escalate at a level that you don't expect, that the performance of the application goes well for a little while and then it degrades, or that the performance is abysmal from the day it goes up into the cloud, or a combination of these issues. Performance issues become amplified when you move your business applications to the cloud. If you have performance issues, you should solve them before moving the applications. And let's take a look and see why this is the case. In this particular example, we have in Azure a virtual machine, and it is associated with Azure Premium Storage. We're also assuming that I/O caching has been enabled for the attached disks, and that I/O caching has been enabled for read-write cache. And thus, when the application writes data and sends it out of the kernel to the cache, the write occurs first to cache and then to the premium storage. Sounds good so far, except for some problems that can be introduced into the architecture if you have an application that is consuming a lot of I/O. And in this particular case, the output of the application is 6,500 IOPS, and the VM is sized at 12,800 IOPS. And thus data writes to the cache and then is spooled out to the Azure Premium Storage. And for all appearances' sake, we do not appear to have a problem because we're not exceeding the rate limit. The problem that comes into play is when the IOPS exceed the rate limit of the virtual machine. And when this occurs, the I/O cache begins to fill. How aggressively the I/O cache fills is entirely dependent on how much more the application is sending to storage in the form of IOPS over the rate limit for the virtual machine. And if this continues for too long, the cache will continue to fill. The application appears to not have a problem, but there really is a problem that's going on here. If the IOPS that are being consumed or written to the cache continue to exceed the rate limit of the machine. And here's where the problem happens. Once the I/O cache is filled for the premium storage, all I/O stops on the virtual machine and the application comes to a screeching halt. And when this situation occurs, with I/O stopped, the I/O cache drains to the premium storage at not more than the rate limit of the virtual machine. Once the I/O cache has drained, I/O resumes, and the I/O cache begins to fill again, so long as the number of IOPS being written by the application exceed the rate limit for the virtual machine. Now I note in the previous slide that the delay can be for several minutes, and this is because the I/O cache is quite large. So imagine several gigabytes being drained from the cache when I/O stops with a small database block size, and how long that could take. It could be several minutes without the application operating at all. And this is not a livable situation. You could certainly solve this problem by increasing the size of the virtual machine. By going with a larger machine with a higher number of IOPS, you could sustain the 24,000 IOPS write that's occurring by the user application. Note, however, in this situation, you could be artificially increasing your cost if the root cause is an inefficient configuration of a database and an inefficient configuration of a kernel. Tune the kernel, tune the database, solve the problem, and then find out how many IOPS you really need for the application. So how can you determine how efficient your I/O is on your database server that you're about to migrate into Azure? So what you're looking at now is the output of vmstat on our database server. And we can see that we have some weight. It's not particularly pronounced. It's for a short period of time. And we have a moderate amount of I/O. And we have no swapping of any kind. We've got a reasonably sized free list. And our cache is large for I/O. However, because we have a significant amount of free memory on the stack, the concern with the cache being large is reduced. We have very little in the run queue, and we have nothing in the block queue. For all intents and purposes, this appears to be a machine that is optimally tuned and running very well. Let's have a look at the opposite scenario, where the database server is not healthy. Here we see that our situation is not good. We can see that we've got a moderate amount of weight on the machine, although we can see the weight becoming more pronounced here. But note that the size of our swap, or the amount of virtual memory that has been swapped to storage, is quite high. This is a big concern. Also, look at the free list and see how small it is and how large the cache is for I/O. It's much larger than the previous system that we were looking at in ratio to the amount of RAM on the free list. We could see evidence of actual swapping of virtual memory into the system and out of the system. And what I mean by the system is the kernel. And we have some block activity in the run queue. And we have quite a bit of activity in the run queue itself. With the exception of the swap here, this does not appear to look too bad, except for right here. But let's go further into the data sample and have a look. This is several hours further along into this data sample with vmstat. And we can see that the situation is not good. We have a very small free list, and we still have a large amount of swap. And cache is quite big. But look at this swapping out that's occurring, where virtual pages are being swapped out of physical memory and into storage. Look at the rate of swap that's occurring. And as the swap activity settles back down to zero, that our free list has grown substantially. But oh, look at this. Our cache has also decreased. What we're seeing the kernel do here is known as page stealing, where pages are being aged out in the cache and RAM is being restored to the system. We see that physical swap on the machine has remained constant, but it's still quite high. It's evident that the page stealing that's occurring on this system is from the I/O cache, not from the physical swap. However, vmstat records from the kernel this activity as swapping out. Slightly back in the dataset, we can see a more stressful situation occurring on this database machine. We can see that we have an elevated weight on the system, and that overall we're spending quite a bit of time on system CPU, and overall the time share of the CPU is more heavily weighted for system time versus user application time. We can see that we have a lot of swap activity going on. And look here, the size of the swap is growing in physical storage. And the memory free list has a significant amount of variance that's occurring while this swap activity is taking place. Again, all of this is an indication of a database system that is not healthy. And if we were to migrate this system as it is to the cloud, we would find ourselves to be in a large amount of trouble. We also need to look at the unhealthy database server from a holistic view in the form of historical graphing or representation of the data set. The data set from the client's unhealthy database server was taken using IOSTAT and VMSTAT in 6-second intervals over the course of 12 hours. And we can see that the I/O weight on this machine is quite elevated. And we can actually see a peak here. And we can see an I/O weight as high as 67 at the midpoint of the data sample. The swap report is certainly another story. Look at this incredible amount of swapping that's occurring in blocks per second. It's pretty high here. That's really high there. And we're looking at real data. We're not making this stuff up. In this view, we've taken out those extreme highs, and we're looking at about a 4-hour sampling period. And we can see that we have constant swapping that's occurring on the machine. And for total IOPS for the machine, we can see that we're getting I/O. Here you can see we have a peak of 18,000 IOPS. But overall, the I/O is many valleys with a few peaks. In this view, we can see the number of I/O operations that are waiting for write. Meaning, in this case, we've got over 120,000 operations that are in queue that have not yet written to storage. The data for latency on this machine suggests a very bad situation. Here we can see latency exceeding 1 second. Or in other words, I/O that is taking a second or more to respond. So in this case, I/O requests are taking over 3.5 seconds to receive a response from storage. Now back to some raw data. We can see that this computer has 66 gig of physical memory. We know it's virtualized because the client told us that. And we can see the amount of memory that is being used for cache is 62.5 gig of the 66 gig of RAM. And the number of pages that are inactive are almost 58 gig in memory. We can see that we've got a total swap size of 33.5 gig and approximately 1.76 gigabytes of the swap space is being consumed. We then looked at the client's Oracle initialization file for Oracle database, and we found that the size of SGA on the machine is 1.67 gig, that the stream pool size is 536.8 meg, and the amount of memory reserved for large I/O operations was set to 0. Additionally, we found that the Oracle database was not configured to use direct I/O. And this is crucial because Oracle is caching I/O in this case, and so is the kernel. And this results in an extremely inefficient situation. Furthermore, by not using direct I/O, we were introducing a situation where the kernel would swap out portions of the Oracle database application and the SGA into the swap space. And this situation creates extreme stress and extreme inefficiencies on the machine, as we have seen from the previous graphs and from the data. Solving this kind of database performance problem requires increasing the amount of memory that Oracle database is using. Hey, you guessed it, you're going to increase the size of SGA from less than 2 gig on this machine to 32 gig. And you'll use direct I/O. By using direct I/O, you will eliminate all swapping on the machine, and you will vastly improve response time to user applications. Your functional users will be happy. Furthermore, you'll have a good idea as to what your I/O requirements really are, and you'll be able to properly size that virtual machine in Azure and pay only for what you need. During this instructional video, we talked about the risk of migrating an untuned database system to the cloud and the importance to fix performance issues prior to moving your applications into the cloud. We talked about how Azure Premium Storage I/O stops when the read-write cache fills. We examined an Oracle database system with an inefficient storage configuration, and we covered measures that could be taken to improve Oracle I/O performance by tuning the SGA. Finally, we talked about the importance to properly size I/O for your application to migrate it into the cloud only after you have optimized the performance of the system. We hope you found this instructional video to be helpful in preparing you to make your move to the cloud. Do you need help getting into the cloud? Classy Design USA is here to help. Call us today and talk to one of our cloud engineers. We'll be more than happy to help. We can be reached at 855-442-5683. Thanks, and have a wonderful day.